All right, AP Calc, here we get going into section 3.10. Good news is this is the last section of the first semester that we are going to be covering, so yay! Bad news is it's a relatively tough section. As you can see from the left side of my screen right now, we only have 3 problems that we're going to be working out here today, but they're relatively tough. So related rates you'll notice here the authors always tend to put this in chapter 3, and I like to cover it at the end of chapter 4, because in chapter 4 we're talking about applications of the derivative, and that's really what's going on in this section. Now, before we go any further, we should probably take just a second and maybe retitle this section just a little bit more specifically. It's called related rates, but what we really ought to do is put a related rates of change at the end of this. And what I'm hoping then becomes obvious, everybody, is that when we're talking about rates of change, excuse me, we're talking then about derivatives. So in these problems, we're going to be talking about different quantities that are certainly related to one another, but whose rates of change or whose derivatives, again, are related but not necessarily the same. Okay. All that talk isn't really going to help us understand very much what's going on, so let's dive into our first example. What's going on here, guys? Water is flowing into a conical tank, meaning a water tank in the shape of a cone with a radius of 5 feet and a height of 10. So we're talking about a pretty big cone here, guys, maybe something in a factory or a gas tank or something like that. And water is flowing in at a constant rate of 15 cubic feet per minute. The question now is, it's actually a 3-part question, how fast is the water level rising when your height is 2 feet or 6 feet or 8 feet? Now, just diving into that question and thinking critically about what it is that they're asking, there's kind of an implication here that there might be different answers to this question for how fast your water level is rising at different heights of the water, meaning that it might change. So to try to get a sense for what's happening in this problem, I want you guys to think about going to your kitchen sink and turning on the water, okay, and leaving it alone. And the idea then would be that unless somebody is flushing the toilet, water should be flowing out of your kitchen sink at a constant rate. Now, I want you to imagine that you're going to take a glass out of your cabinet or cupboard, and you're going to hold it underneath the water, and you're going to fill that glass up. Now, if your glass is a cylinder, which a lot of kitchen glasses are, or at least they're pretty close to it. If your glass is a cylinder that looks something like this, okay, I want you to think about what is going to happen then, everybody, to the level of water within that glass. Now, depending on how high you've turned on the water, let's just say for the sake of argument that after 1 second, your water level is right about here. Okay, that's how much water we've got in there after 1 second. Maybe it went up 1 inch for your water level right there. The question I have for you is, where's the water level going to be after 2 seconds? And I think you guys can see pretty clearly the water level is going to be twice as high now after 2 seconds as it was after 1 second. And after 3 seconds, it's going to be 3 times as high. And the point here is that in a cylinder, everybody, our water level is rising at a linear rate. The reason why is because every one of these circular cross sections of water, if you think about these little circles that I'm drawing representing the surface of the water at different times, every one of those circles is exactly the same size. So therefore, the water level is going to rise very predictably, assuming again, of course, that our water is coming out of the kitchen faucet and into this glass at a constant rate. Now, that's what happens if you're filling up a cylinder. So whether it's a glass or a cylindrical tank, okay, it'd be pretty predictable and pretty simple. But what's happening in this problem, guys, is that we are instead, and I'll erase this and draw it better in a minute, but we are instead filling up a conical tank, one that might look like this. And anybody who's ever filled a little plastic cone of water here out of a cooler you might have on the soccer field or at the golf course or something like that, these are the little cones you pull out of the side, like a little snow cone basically. So what happens here? After 1 second of filling up your water, I have no idea, but I'm just going to guess right here, guys, maybe your water level is right about here. That's where it is after 1 second. Now, my question for you guys was going to be now, where is it going to be after 2 seconds? All right, so I'm just guessing here, but if the height of that water within this tank right here was, again, something like 1 inch, do you think we would be at 2 inches of depth after 2 seconds? And I'm guessing that 2 inches of depth might be right over here. The answer to that, I think you guys can see it, would be no. And the reason why is because the volume right here in this, it's not really a trapezoid, but you know what I mean, that volume is a lot greater than this volume right down here. All right, so because the cross-sectional area within a cone is not constant the way that it was in a cylinder, it might well be the case that after 2 seconds, maybe our water level is only about here. And that's where we are after 2. And after 3, there's probably even less of an increase than there was between 1 and 2. And after 4, there's probably even less of an increase. So what's going to happen here, guys, as we fill water out of our kitchen sink into this conical tank right here, that water level is going to rise very quickly early on, and then it's really going to level out and slow down as we get near the top. So, how does that relate, related, to what it is that we're talking about here today? Well, lucky for you guys, everybody, there is kind of a process for how we go about doing a problem like this, and let's see if we can't walk our way through it. So again, let me draw your attention back to the title of this section, related rates, or related rates of change, or related derivatives. So here's what we need to do first. We need to identify what variables we're dealing with, or what quantities we're measuring within the life of this problem. So what's going on here, guys? We've got water flowing into a tank at a constant rate of 15 cubic feet per minute. Now that is a rate of change, everybody, cubic feet per minute. And it's a derivative, therefore, and it's one that we were given. So I always like to start these problems by writing out what derivative we know. And 15 cubic feet is a measurement of volume. Minutes is a measurement of time. So we were given the derivative of volume with respect to time, dv dt, as 15 cubic feet per minute. The units, everybody, are going to tell you what derivative you know. Cubic feet per minute is a measure of volume over time. So that's why we know dv dt. Now, in addition to these problems, there's also a derivative that we want to know. So let me find the question, usually the last sentence in these problems. How fast is the water level rising? Water level. When we talk about the level of water in a tank, we're talking about the height of the water. So we are looking for the derivative now of height taken with respect to time. But I've got to warn you that the way I have this written right now isn't really accurate. And the reason why is because, and I think I can tell from the way the question was worded, this quantity right here, the derivative of height with respect to time, is not constant. We just got done saying that at the bottom, as you're filling this up, the height level is going to rise very quickly. But as you get higher up, the rate at which your height is increasing slows down, unlike a cylinder where that was always going to be the same. So I want to be a little bit more specific here, and I want to say that I want the derivative of height with respect to time at the moment when, and here's the first question, one at a time, guys, when h is equal to 2 feet. Okay. So this is the derivative that we know, dv dt, the derivative of volume with respect to time. This is the derivative that we're trying to find, the derivative of height with respect to time. And so what we need eventually is an equation that relates this derivative with this derivative, related rates of change, or related derivatives. That's what we're going for. But before we can talk, everybody, about an equation that relates the derivative of volume and the derivative of height, we need a simpler equation that just relates volume and height. Those two things all by themselves. So I'm going to start a new page right here. No, I'm not. I'm going to do that. That's what I meant. Okay, guys. And this is one of those formulas that Mr. Fontana, the longtime geometry teacher, is really going to feel like you guys should know on your own. But lucky for you, this would be given to you at the beginning of a problem, everybody. The formula for volume of a cone. Well, all cones and pyramids for their volume have a 1/3 out in front. Then it's the area of its base, which is pi r squared, it's going to be a circle in a cone, multiplied by its height. So that's the formula for volume of a cone. Now, what I want you guys to notice, though, that's tricky, is that this is a three-variable formula. We've got a V over on the left, and then we have an R and an H over on the right. Now, that's a problem for us, because if we go back to our little list right here, we know dV dt, the derivative of volume with respect to time. So I'm fine with that V being there. We are trying to find, back to it here, dH dt. So I am fine with that H being there. The problem, everybody, is the R. If I tried to differentiate or do anything with this equation right now, I would need to know the value of R, or eventually the value of dr dt. I don't know that. I don't want to know it, so that's a problem. So what we're going to do is take advantage of a fact of geometry right here that I think you guys know, although I'm not sure. And that would be that no matter what the water level is within this tank here, whether it's pretty low like this, or higher like this, or even higher like this, all of these triangles that I'm drawing, guys, I'm hoping you can come up with the word before I tell you, all of those triangles are similar triangles. Same shape, but different sizes. Okay? And that means that there's always going to be the same relationship between the radius of water right here on the top of that surface and then the height of the water, or the depth, measured over here on the side. What we need to do is draw a relationship between R and H so that we can represent one of those quantities in terms of the other. So, regardless of whether or not this tank is half full, a quarter full, completely full, the ratio of radius to height when we measure the water at any spot is given to us by the same quantities or the same measurements right here that when the tank is full. So when the tank is full, the radius of our water would be 5 feet and the height of our water would be 10 feet. Now that same ratio, everybody, 5 to 10, which of course simplifies to 1 over 2, would apply at any radius and height level in this water. For example, when the height of your tank, not the tank, when the height of the water in the tank was only 2 feet, the radius will always be half of that, which would be 1 foot. When the height is 6 feet, the radius of water would be 3 feet, and so on and so forth. So here's our ratio, guys. Now, what we want to do next, R over H equals 5 over 10, we want to solve this right here for one of those two variables right here. So, probably a good idea to go ahead and cross multiply here and get 10R is equal to a 5H. And before we go any further, let's review what we said before. The problem in this equation right now is the R. We don't know dr dt. We're not asked to find dr dt. So we've got to get rid of R. That means we solve this equation here for R by dividing both sides by 10. And we're going to get radius is always equal to, and that 5 over 10 is going to be a 1/2 h. Box that quantity up, everybody, because that is really important. And I can't say this plainly enough. You cannot get a related rate problem correct unless, in a problem like this, you correctly establish the relationship between the two variables so that you can get rid of the one that you don't know and you don't want, and that would be R here. So no matter how much water is in the tank, the radius of the circle of water that we see on the top is always going to be 1/2 the depth or the height of that water. So now that we know that R is equal to 1/2 h, we can go back over here and we can make a substitution. We can now say that the volume of that cone is equal to, here we go, we have got a 1/3 times a pi. The radius we just got done saying was a 1/2 h. So there's your radius. Don't forget to square that radius, and we multiply that by h yet again. So I'm going to go ahead and clean that up a little bit, guys, and do this on the same line. The 1/2 squared is going to make a 1/4, and I multiply that by the 1/3 out in front to get a 1/12. The pi can stay right where it was, and take a look at what's going on here, guys. This makes some sense. H is being squared, and then multiplied by h again. That's going to get you a 1/12 h cubed. And not to point out the obvious, some of you I know get this plain as day, but others probably have never thought about this before. What we've come up with right here, guys, 1/12 pi h cubed is a formula for volume. And if you think about what volume means and what units volume will always be measured in, those units have to be cubic units. And what's going on here? Our height, which would be measured in linear units, such as inches or centimeters or feet, is now going to get cubed. So in this case, it's going to be feet cubed, and that's going to get you cubic feet, which is the measurement that we're looking for volume. All right, guys, we have accomplished something important here. If you look at just what I've double underlined here, volume on the left is equal to a 1/12 pi h cubed on the right. That's the equation that relates volume with height, V with h, and nothing else. So we are now ready to take the derivative of that equation. And I want to take you back real quick to this messy first page and remind you that the derivative we know is the derivative of volume, but with respect to what variable? T. This was cubic feet per minute. And the derivative we want is the derivative of height with respect to T. It's dH dt. Therefore, when it comes time to take this derivative, the question is, what are we differentiating with respect to? And the answer in a related rate problem is pretty much always T. So this is not a step we usually show, but we're going to take the derivative with respect to T of the left side here, and that's going to equal the derivative with respect to T of the right side. And hopefully this sounds a little familiar, guys. This is implicit differentiation. We're differentiating with respect to a variable other than the variable presented in the expression. So here we go. The derivative of volume with respect to time is simply written as dv dt. Gotcha. And on the right-hand side, remember that with implicit differentiation, you basically do what you've always done before. You basically say, okay, what would the derivative of 1/12 pi h cubed be taken with respect to h, that variable? So the power rule says you'd multiply the 3 out in front. The 3 times the 1/12, that's 3/12, which is 1/4. Gotcha. Pi is a constant, so it just tags along, and the h cubed now becomes an h squared. But wait, there's more, times the derivative of the base of that exponent. And the derivative of h taken with respect to t is dH dt. So that equation right here that we just came up with, guys, our derivative is finally the equation that relates the two derivatives, the one that we know, dv dt, and the one that we want, dH dt. So finally, took a long time, we finally got an equation now that relates our two derivatives, or our related rates of change. Now, what I need everybody to understand is that this equation has 3 variable quantities. dv dt on the left, that's a variable quantity, even though it's a derivative. We have an h in the middle of the right side, and then a dH dt on the far right. Out of those 3 variable quantities, we better know the values of 2 of them so that we can solve for the third. And we do. dv dt, it told us in this problem, was at a constant rate of 15 cubic feet per minute. Water is flowing into the tank at a constant rate. So it doesn't matter when or where we are, dv dt is constant at 15 cubic feet per minute. That now equals a 1/4 times a pi. And this h right here is tricky, guys. This h is what we're going to call a time-specific value. The height of the water in the tank is not always the same. It's changing. And that is why, right over here, I thought it was a good idea to write this down. We are looking for dH dt, but at a specific moment in time when the height here is equal to 2 feet. It's not always the same. As I think you can see, this value depends on this value here. So we were first interested in when the height of our water was 2 feet. So I'll put a 2 in there for h and square it, and then we'll multiply that by a dH dt. So what happens here, guys? We can clean up that right side just a little bit. The 2 squared is going to be a 4 times 1/4, conveniently is just 1. So this is pi times dH dt. And since we were looking for the value of dH dt, we would simply divide both sides by pi and get dH dt is equal to a 15 over pi, and that's our answer to this question. Now, just for fun, if we were to talk a little bit about units, let me go back a couple steps. You do not need to do this, everybody, but the derivative of volume with respect to time was 15 cubic feet per minute. Okay, think about what's going on then now. That 2 right there was measured in feet. All right, so, but then that's getting squared as well here. So we end up with kind of a pi, and that's more like square feet over here. This, again, was cubic feet per minute. And what's happening now is we're taking 15 cubic feet per minute and dividing that by square feet. And what happens here? 2 feet cancel top and bottom, and we end up with just feet per minute. That's the unit right here for this answer, guys. 15 over pi feet per minute. And if you think about it, feet per minute is a pretty reasonable unit right here for the rate at which your water level might be rising. So, lots of extra junk going on right here, but this is the answer to the first part of that question. Now, real quickly, I just want to put a bow on this one. You'll notice if we go back to the original that I actually asked you 2 more questions. How fast is the water level rising now when the height is 6 feet and when the height is 8 feet? Good thing for us, 90% of the setup work we did here is exactly the same. Everything, including the setup, the relationship here between R and H, and the derivative equation, all of those things are the same. It's just now a question of putting in a different value for H. But I did want to remind you guys, if we go back to this example right here, that diagram of filling up a conical tank, that the higher the water level gets, we said before that the water level should be rising at a slower rate the higher up you go. So when I do this real quick with a height level of 6 feet, we should see an answer that's less than the 15 over pi that we came up with before. So let's try all that again, guys. Going back to, let's see, let me rewrite this equation here at the top in the center. So dv dt was equal to, oh shoot, was that a 1/4? Yeah, 1/4 pi h squared and then a dh dt. And I'm writing that there because I'm going to do 2 more problems real quick here. So the first, or the next one we're going to do is when h was equal to 6 feet. So what's going on here, guys? dv dt was still 15. That was now going to equal a 1/4 times a pi times h squared. Well, 6 squared is going to be a 36, and we're looking for a dh dt right here. I'm going to do this kind of quickly in my head, guys. The 1/4 times 36 is going to end up being 9, so we're going to end up then with, ooh, not like that. We're going to end up with a dh dt is equal to, that'd be a 15 divided by a 9 pi. Okay, gotcha. And I guess we could simplify that by dividing a 3 out real quick and get a 5 over 3 pi. But regardless, that's that answer. And if we think about how that compares to this answer right over here, 15 over pi was our first answer. Let me look here. 15 over 9 pi was our second answer. Our denominator got bigger, and that means that the value of our fraction actually got smaller, and that's what we thought would happen. And then I think the last one I asked you was what happens now when the water level in the tank is 8 feet. So in this case, guys, it would be a 15 equals a 1/4 times pi times your radius squared. That'd be a 64 and a dh dt. Okay, the 1/4 times the 64 is going to be a 16, so we would end up now with dh dt is equal to 15 over a 16 pi, and that would be this answer here. And again, look at this answer that we got when the height was 6. Look at this answer we got when the height was 8. As the height increased, dh dt, the rate at which the water level rose, decreased yet again. So the higher your water level gets, the slower it's rising. All right, guys, so that is our first related rate problem. Whew! Loads of fun, huh? All right. I think I'm going to stop this video right here and do this one in 3 different parts right here, just one for each problem because these take so long. So we'll come right back and we'll work on problem number 2.